Hello everybody, let us now continue our discussion from where we left in the last lecture. In the last lecture we were discussing about the host gas inclusion property of calixarenes, where we saw that in calixarene we have got polar regions, we have got a central non-polar region, and there is preferential interactions depending upon the nature of the guest with either the polar regions as well as the non-polar regions. We looked at the role of cations. For example, we looked at small cations which interact with the oxophilic region and the larger cations which preferably interact with the pi surfaces. Then we looked at the different conformations of calixarene and so on and so forth. Now today we are going to discuss about another very interesting class of compounds which are very important and very popular in the applications industry, which is called cyclodextrins. So cyclodextrin are very important molecules and they have got different applications. One of the most important application of cyclodextrin to start with is that it is used as a packaging molecule. Packaging in the sense that it is used for packaging different kind of dyes, pigments, drug molecules and so on and so forth. One particular example I would like to emphasize here is, for example, in the drug industry, the packaging of the drug molecule with cyclodextrins is very important. So most of the time what you have is that a drug molecule which is not very soluble. So in order to make the drug highly soluble, it is now packed into this cyclodextrin capsule or the cyclodextrin powder, and then this cyclodextrin powder is able to contain, it's essentially a molecular container which has got an intrinsic cavity. This cavity is present either in the solid state or in solution, similar to what we observed in case of calixarene, and it has got a void which can now contain the drug molecule, and this drug molecule is then released at the site of action once the cyclodextrin goes and dissolves into the gastrointestinal tract. So it can modulate, cyclodextrins can now be used to modulate the solubility profile of the drug, and it is also an excellent biological transport molecule. That is, it can transport the drug at the site of action in a very efficient way. Now, why is this particular property very nicely achieved in case of cyclodextrins? So let us look at what are cyclodextrins. Essentially, these are cyclic oligosaccharides comprising of either 6 or 7 or 8 D-glucopyranoside linkages. So there are 6 such D-glucopyranoside linkages. That is, the essential building block is the D-glucopyranoside, and they are essentially linked by the 1,4-glycosidic bond. So this is to start with the chemical composition of cyclodextrin, and they have got a very rigid pre-organized host. They have well separated polar and non-polar regions. That is, we can say these are hydrophilic and these are lipophilic or hydrophobic. So we have got two distinct regions similar to that of calixarenes, but they are very much rigid and pre-organized. And some of the most important properties of cyclodextrins is, as I told you, it is very important in the food industry, the drug industry, and what is very important when it comes to application is to look at the economic viability of the compound. That is, how easy it is to make the compound, what is the how easily it is available, what is the cost of making this particular packaging molecule. And it has been observed that in case of cyclodextrin, large quantities and large tons of cyclodextrin have been produced at very nominal cost. So what makes it attractive is that it is economically viable, and so the cost of production is less. And this is very important when it comes to the drug industry, because we have to keep in mind that it's important to look at the fundamental aspects of supramolecular chemistry, but when it comes to translation or achieving an application, a desired application to reach the market, then the cost of production becomes a very, very important factor. And here the cost of the packaging unit, in this case the packing molecule, which is going to modulate the different physical and chemical properties of my drug of interest, should be economically viable. And the second most important thing is that because you are going to package this particular molecule and bind it with the drug using non-covalent interactions, it should be entirely non-toxic, because any chemical component which goes into the body can have a certain toxicity, but in this case this is extremely non-toxic over the entire dosage range, over the entire dosage range of the drug molecule. The third thing is that it is a fully saturated molecule. There is no pi bonds present, that is, there is no unsaturation. So it is purely a sigma framework driven molecule. So it is fully saturated. And let us now look at the structure of this particular compound. How does this particular molecule look like? So we can draw the corresponding cyclodextrin to start with. So we have got 1, 2, 3, 4. So we have got the OH here, we have got the OH here, we have got the primary group here, OH here, OH here, primary one here, then we have got the primary one here, primary hydroxyl group here, secondary hydroxyl group here, and similarly we have got the primary group here as well as the primary group here. And we can add the corresponding OH as well as OH. So you can see very clearly that this is a 6 units of D-glucopyranoside linkages, and this constitutes the alpha cyclodextrin. So I'm sorry the diagram is not very beautiful, but essentially it highlights the representation of the chemical structure of alpha cyclodextrin. What is important to realize is the stereochemical disposition of the secondary hydroxyl groups. These are the secondary hydroxyl groups, and these are the primary hydroxyl groups. So these are the primary hydroxyl groups, and these are the secondary hydroxyl groups. And you can also see that they are connected via the glycosidic linkage, that is 1, 2, 3, 4. Okay, so this is the connection. This is the 1 position, 2, 3, and 4 position, and again this is 1, 2, 3, 4. So they are connected via the 1,4 glycosidic linkage, and these are essentially the carbohydrate moieties which essentially connect to each other to form this 6-membered to form the 6 units of D-glucopyranoside. Now when the number of units are 7 units, this is referred to as beta cyclodextrin, and when the number of units increases to 8, it is referred to as gamma cyclodextrin. So we have 3 independent cyclodextrins, alpha, beta, and gamma, and it is important to realize how they look essentially. So we can represent cyclodextrins in a way similar to that of calixarenes. We can represent them as follows. These are more bucket-like molecules which have got this is the hydrophobic cavity, and we have got these are the primary hydroxyl groups, and the secondary hydroxyl groups are on the upper rim. So this is the upper rim and this is the lower rim. So the upper rim and the lower rim have got these hydroxyl groups, and this is the hydrophobic cavity. So this is a very interesting molecule because it has got a very rigid conformation. It is highly pre-organized, and you can see that it has got a spherical curvature, so that curvature is quite sharp, and any molecule which has got both hydrophobic and hydrophilic content can now go and be trapped and can safely sit into the void which is created, or the cavity which is created by this particular cyclodextrin molecule. The drug molecule of interest can be trapped here. Depending upon the shape and the size of the drug, this drug will be included here, and now this cyclodextrin which contains the drug molecule can now be transported, can now be first dissolved. It dissolves and the drug is released at the site of action. So this is the shape representation of a cyclodextrin, and what has been observed is the following. What has been observed is we can now specify some of the most important geometrical dimensions of this particular cyclodextrin, which we call as the anatomy. So what has been observed is that this particular separation is 13.7 angstrom, and then the inner one is 5.7 angstrom. That is for your alpha cyclodextrin containing the 6 units. For the corresponding beta cyclodextrin, because the size is larger, the dimensions increase to 15.3 and 7.8 angstrom, and for gamma cyclodextrin it is further increased to 16.9 angstrom and 9.5 angstrom. That is the outer rim and the inner rim dimensions are given. So naturally, as the size of the rim increases, the size of the cavity also increases, and will be able to put in relatively larger size gas molecules into these cyclodextrins. And some of the most important properties of these cyclodextrins I would like to mention has been actually obtained. Physical properties. For example, number of glucose units. In case of alpha, beta and gamma, this is 6, this is 7 and this is 8. What is the ring size? The ring size is 30, 35 and 40. So, the ring size increases. What is the internal cavity diameter? What is the internal cavity center diameter? That is 5 angstrom, 6.2 angstrom and 8 angstrom. And what is the enthalpy change? The standard enthalpy change in solution in kilojoule per mole is 32.1, 34.7 and 32.3. It increases slightly for beta but drops for gamma, and the entropy change for the solution in joule mole inverse Kelvin inverse, this is kilojoule, is 157.7, 48.9, 61.4. These are chiral compounds. Cyclodextrins are actually chiral compounds, and therefore, the optical rotation values at 25 degree centigrade is 150.5 degree, 162 and 427. And what is the cavity volume? What is the cavity volume in 1 gram of CD in centimeter cube? 0.1, 0.14 and 0.20, and the pK value at 25 degree centigrade is 12.33, 12.20 and 12.08. So, these are some of the most important physical properties of these alpha, beta and gamma cyclodextrins. And now, we would like to look at, keeping in mind these important properties, we would now like to see the host gas complexation behavior of these class of molecules. The host guest complexation behavior. So, now let us look. So, there are we know that when we have got host gas complexation, it is the most important factor is the steric fit between the guest and the cavity of the host, followed by the release of high energy water molecules, and then a combination of hydrophobic interactions between the host and the guest, and hydrogen bonds between the water molecules, which are expelled from the interior of the host molecule into the bulk. And we know that this is favorable on both enthalpic as well as entropic grounds. So, keeping this thing in mind, what has been investigated is the binding of different guests, the binding of different gas of alpha CD in water. So let us take different molecules here. For example, we have taken this nitrophenol, then we have taken the phenoxide ion, the nitrophenolate ion. This is the nitrophenolate. Then we take the hydroxyl compound, which now contains two 6 substituted methyl groups. So this is the methyl group here and the methyl group here, which is at the 2,6 position. We take the corresponding phenolate ion as well, and then we change the position of the methyl groups to 3 and 5, and also take the corresponding phenolate ion for these compounds. So now we have taken 6 different guess 1, 2, 3, 4, 5 and 6, and what is reported are the log K values. The log K values are 2.32, 3.36, 1.78, 3.07, and practically there is no binding observed when we have got the 3,5-dimethyl nitrophenol, or we have the corresponding phenolate of the same compound. We see that practically there is no binding between this particular guest molecule with the host, that is the alpha cyclodextrin. So then it is important to understand that how are the trends in this log K observed. So what is to start with, the first observation is that the binding of the phenolate ion is in general greater than that of the hydroxyl compound. So when you have the phenol, the binding is lower compared to that of the phenolate ion. So that indicates enhanced hydrogen bonding. So this indicates enhanced hydrogen bonding between the hydroxyl groups of the cyclodextrin with the phenolate ion. Okay. So it is not that there is no hydrogen bonding. Obviously there also exists hydrogen bonding with the phenolic groups, but O- has got greater charge density, so the strength of the hydrogen bond is greater, and therefore the binding is also much more greater. So what is the structural model which has been proposed to account for this thermodynamic data? It is as follows. So let us consider this to be the cavity, and this is the molecule which comes and sits here, and we have got, as you see, we have got in the structure I showed you, we have got the secondary hydroxyl groups which are on the upper rim and the primary hydroxyl groups in the lower rim. So we have got these secondary hydroxyl groups here, but we also have the water molecules, but we also have the water molecules which can not only extensively hydrogen bond with the secondary hydroxyl groups which are exposed on the rim, but they can also hydrogen bond with the O- ion. So there is strong solvation, very strong solvation of the host guest complex, and definitely because the upper rim is wider, there is much more space available to accommodate now the methyl groups. to accommodate now the methyl groups. You have got much more space available, and these methyl groups can be easily accommodated in, so this particular guest can now be easily accommodated here. And but now when the methyl group is present in this position, then there is a steric clash. There is a steric clash between the hydrophobic cyclodextrin cavity and methyl groups. So this particular molecule here, they are not able to get included into the cavity, because the size of the cavity, as you go into the cyclodextrin, the size of the cavity decreases, and in this particular molecules, the span of the molecule is more, because the methyl groups are exposed and it has a greater span. So because of this, it does not have the right steric fit to be included into the cyclodextrin cavity, and therefore there is no association of these guest molecules with the cyclodextrin host when we have got methyl groups at the 3 and 5 position. So this is a very interesting case where you can actually put methyl substituents at very specific positions and modify the hydrophobic nature of the guest such that it can still undergo host guest complexation with the cyclodextrin cavity. And you can, instead of taking these kind of phenolate groups, people have also now taken CH3, CH2 whole n X. You can also take these kind of groups where X is equal to fluoro, chloro, bromo, and you can have hydrogen bonding between this X with the water molecules which are exposed, as well as the OH groups of, or the secondary hydroxyl groups of the cyclodextrin moiety. Now, it is important to keep in mind that we need to have a strong solute solvent, we need to have a strong solute solvent interaction with the solute now is the host and the guest together. So, you have the stabilization of the host guest complex in solution, but many times in many cases the host guest complexation itself are not very favorable, and in that case what happens is that we are able to get crystal structures of cyclodextrin. We are able to now get crystal structures of CDs, that is different arrangements. And sometimes what happens is that the size of the size of the drug molecule or the size of the guest molecule is large, but your cyclodextrin does not have a big size cavity. Now what happens is that the cyclodextrin now gets included in the crystal structure. It forms a layer of molecules, and now this layer has got larger size voids, and therefore we can now pack in more amount of molecules, or we can include slightly larger size guest into this particular host as well. So the packing, the crystal structures of cyclodextrin have got different packing arrangements, and we can now consider, for example, the head to tail arrangement, where we can have to start with, I would first represent the head to head arrangement. So you can see here that this is the head, this is the tail, this is the head, this is the tail. So you have got a head to head arrangement of these cyclodextrin moieties inside the unit cell, and then they can repeat themselves. So this is one particular head to head arrangement. We can have the head to tail arrangement. So this is second one. We can have the head to tail arrangement For example, we can have it in this way. This is the head, this is the tail. Now we again have the head and we have the tail. Then we again have the head, we have the tail. And we have the centrosymmetrically related component as well. So you can now see this is the head, this is the tail, this is the head, this is the tail. So this is arrangement in one direction, this is in the anti-parallel direction, such that they are related by a center of symmetry in the crystal packing. And this again you can say tail, head, tail, head, tail, head. This kind of an arrangement is there. We can also have a layer type of arrangement. Let us look at the third one. We can have a layer type of arrangement where we can see so we form these kind of layers. So this is a layer type of arrangement, okay, where we have this overall layers which are being formed. And we can also have the herringbone arrangement, where we can have okay, so we can have slightly, I would like to change this here. So the idea is that you have got this one layer in one arrangement, this is in the perpendicular orientation. So this perpendicular orientation is called a herringbone arrangement. And now you can see here that when you have this particular arrangement head to tail, you have this void cavity which extends. You have got this void cavity which extends. Here also you have got the void cavity which extends, but here the void cavity does not propagate. So the suitable arrangements in which the void cavity can extend can now allow you to include slightly larger size guest as well into this particular voids. And what has been observed is that, just to give you a few examples, alpha cyclodextrin, for example, includes benzene, methanol, 1 propanol and 3 iodo-propanoic acid. Whereas in the case of beta cyclodextrin, it has been possible to include benzene, benzyl alcohol, and gamma cyclodextrin includes water molecules by and large. So, so if you want more larger sized gas to be included, then we can take this extended hydrophobic cavity. This is the extended hydrophobic cavity which can now include gas molecules in the cavity. So, with this particular background in mind, now we can look at some of the most important applications of these compounds. So, one application I have told you is in the drug industry, that it is very relevant. So, for example, in analytical chemistry, as I told you, it is a chiral compound, these cyclodextrins. Therefore, they can be used for making chiral columns which can be used for separation of organic molecules. That is one application. They are used in food and cosmetics industry. They are used in pharmaceuticals, and they are also find application in enzymology and other biological processes and other biological processes. So, how does it do this exercise? How does it achieve this desired property? So, as I already talked with respect to the pharmaceutical co-crystals, you can improve the bioavailability of the drug. Because now you can encapsulate put the drug inside this cyclodextrin, and then it can be transported to the site of action. And next thing is that it enhances the stability of the drug with respect to photochemical degradation, moisture, pH, etc. Now, it is very important to keep in mind that the drug industry produces these drugs in large quantities, and these are also transported from one place to another. Now, these are very sensitive. It can happen that the drug is very sensitive to light, it is very sensitive to moisture, it can take up water, and also sensitive to acidic or basic conditions. So, in order to improve the shelf life of the drug, and you would like to enhance the stability of the drug and the shelf life, that is the time for which the drug is being stored before it is being given to the customer for consumption, the stability of the drug can be enhanced by encapsulating this drug in a carrier molecule like the cyclodextrin. So, cyclodextrin definitely enhances the stability of the drug and also the shelf life of the drug, and the resulting cyclodextrin drug complex is a powder which is easy to handle. Okay. The next thing is that it is added as a flavoring agent with different compounds. So, along with the, say you are adding flavoring agent, for example, in the food industry you are adding this flavoring agent. So, then you can mix the flavoring agent with different compounds, which that is the flavoring agents plus this cyclodextrin, and make them more resistant to oxidation, thermal decomposition, and loss by sublimation. So, if the compound of interest, the flavoring agent or the particular organic molecule which is being used has a property of that it can sublime easily, then this encapsulation with cyclodextrin can make it more resistant to this, minimizing the process of sublimation, thermal decomposition, as well as any oxidation process. And so, as you can see now that overall these are some of the most important applications, and most importantly also it is used to make the sun block lotions, that is in the cosmetics, in the different cosmetics which are being utilized. For example, sun block lotion, cyclodextrin has also been added again to increase the stability and to prevent photolytic processes to take place, where decomposition of the compound can take place in the presence of the light. So, I hope with this lecture we have been able to understand the importance of cyclodextrin, and this essentially completes host gas complexation behavior. And now we will go, from next week we will go on to the next module, which will talk about crystal engineering and other aspects of supramolecular chemistry. Thank you.